Okay. Okay, so let's take a look here. Okay, imaginary numbers. Now this is, I'll quickly, we got through quite a bit of stuff. It's been a few days though, actually it's been last week. So complex numbers. We said that I, this weird thing called I, we defined as the imaginary unit. And we just said that's equal to the square root of -1, right? Nothing new there. We use this as a way to represent square roots of negative numbers. Now, they're not real numbers. We can't take the square root of a negative number and get a real result. We get this imaginary result instead. So it's a different category, different set of numbers. But they still exist, and I still want you to give me those answers. So what about these properties of square roots of negative numbers, these i's? Here's how we use this. If I have the square root of a negative number, then we know that we can split that up into the square root of -1 times the square root of r, right? And the square root of -1 is just I. So we can take a little shortcut then. Whenever we see the square root of a negative number, we can just factor out the square root of -1, and we know right away that's going to be an I. And what we're left with is the normal old square root of a positive number that we'll deal with just like we did in section 3. Okay, we can simplify it if we want to, but that's what we get. Okay? So the square root of -r, we're going to know now that's just I times the square root of positive r. So some examples. What would the square root of -3 be then? I times the square root of 3. Sure. We're just going to take out that square root of -1 and call it an I, and we're left with a normal square root of positive 3. Okay? Yeah, I times the square root of 4. And what is the square root of 4? 2. So just 2I. Right? Okay? Good. Okay, so then, and we said that we can look at various powers of I. And we're going to end up simplifying this into a real easy scheme. If I is defined as the square root of -1, then what's I squared? If I square both sides, I get I squared. If I square a square root, doesn't that just cancel the square root out? So what? -1. Okay, so I squared is -1 always. That's going to be important to us when we multiply complex numbers. So I cubed would just be I squared times I. So I squared is -1 times I is just -I, right? I cubed is -I. I to the 4th, easiest way to do that would just be I squared squared. -1 squared is what? 1. I to the 4th is 1. And then I to the 5th starts the whole cycle over again. I to the 5th is the same as I to the 6th is the same as -1. I to the is the same as I squared, sorry. I to the 7th is the same as I cubed. I to the 8th is the same as I to the 4th, etc. As far as you want to go. So if we want to do something weird, take an arbitrarily big power of I, like say I to the 23rd, all we've got to do is see where are we in this cycle. So we just ask ourselves, how many times does 4 divide into 23 evenly? 5. We don't really care about that so much. What's the remainder? 3. So if the remainder is 3, then I to the 23 is the same thing as I cubed. We just care what the remainder is when I divide 4 into that power. So I cubed is -I. End of story. All we have to know then are the first 4 powers of I, and that's it. Those answers are just going to be repeated forever. Okay? So no big deal. No big deal. Now remember that, let's look at some examples of what happens when we square out an imaginary number, like I times the square root of 3. Now this takes us back to some stuff that we haven't probably done in a while. So we have to know, in order to do this problem, if I have the quantity A times B to the n power. How do I deal with that if I have a product to a power? What do I do with the exponent? I distribute. Now here is something you got to really pay close attention to, because this is probably one of the top 3 or 4 most common mistakes people make at all levels in math. This is equal to a to the n times b to the n. I distribute the exponent, but don't confuse that with this. A plus b to the n is not. That is not equal to a to the n plus b to the n. Unfortunately, what it really, and we won't talk about this for a while, we're going to get into this stuff later, but what this is actually equal to is a plus b times a plus b times, see what I'm doing with that? I've got to have a string of a plus b's times a plus b's n times. You've got to have n of those all multiplied together. That's a horrible mess. And that's called a binomial expansion. We won't get there for quite a while. But this, it turns out, is much, much harder than this. If we're just taking a product, a times b to the n is easy. That's no big deal. A plus b to the n, much harder. Okay, make sure you remember that key difference. Okay, so this first one then, if I distribute the squared, I'm just going to get I squared times the square root of 3 squared. Oh, square or square root, what's it do? Cancels. So I'm going to get a 3 here. What's the I squared equal to? Negative 1. So the result then, negative 3. Okay. Now here's an example of why we even did this in the first place. If we're trying to solve this equation, this looks very much like this is going to be a problem from section 5.3. Right? This isn't easier than 5.2. 5.2, we have to do all that factoring stuff. But in 5.3, we said if we can just point to a single x, like right there, I can isolate it by reversing order of operations. So what are the steps I would go through then to get that x by itself? Okay, subtract 10. Whoops. Good. Divide by 3. Okay, now square root, right? And if I square root, when I get that x by itself over there, what do I have to include on the other side when I square root both sides to solve for x? Plus or minus. That's key. We can't forget that plus or minus. That's another thing that's easy to forget. Now what we're taking, we get plus or minus this, the square root of negative 12. Well, I see a negative sign there inside the radical, so I know right away that I'm going to pull that square root of negative 1 out and make it an I. And then I've just got the plain old normal square root of positive 12. I could go one step further with this. If I want to simplify that radical, what could I do? Make it, okay, 4 is a perfect square that divides into 12. So I could break up the square root of 12 into the square root of 4 times the square root of 3. So that's 2 times the square root of 3. There you go. Good. So I end up with, so I'm going to get plus or minus I times the square root of 4 times the square root of 3. That becomes a 2 times I times the square root of 3. And we would write that. We'd put the 2 first. It doesn't really matter. Just like variables. We'd put the 2 before the x. Yes?
So can you have a negative I?
Sure.
So if you had like a negative I squared, would it be positive 1, or would it still be negative?
If you mean if you had, now there's a difference. Do you mean this? Or do you mean this? Because they're different.
What's the difference?
Well, this is saying negative I times negative I. So if I distribute that squared to the negative 1, a negative times a negative is always positive, isn't it?
Okay, and the other one?
So this just equals positive I squared, which is negative 1.
Okay.
Right? This one is saying, whoops. This one is saying I squared times negative 1. I squared is negative 1 times negative 1.
So they
Equals
still
1.
Positives.
So they are different. Right. See? Okay, so let's go back over here and finish this guy up. Good questions. Okay, so then we could break this up into, plus or minus 2. There's my square root of 4. I times radical 3. Okay. Make sense?
Sure.
Okay. Takes a little getting used to, but it's not so bad. All right, so complex numbers. We said then that this new set of numbers that includes everything, it's called complex numbers. They have a real part and an imaginary part. Remember, we said this is our standard way of writing a complex number. The real part is just the number that sits out in front, and then the imaginary part is the part that's multiplied by I. Okay? There's an example. 5 plus 4i would be just a random complex number. Now, the imaginary numbers that are just plain imaginary numbers can just have the imaginary part. We don't have to have a real part on there, but we can. Okay. A real number, the kind we've always dealt with, is just a complex number where the imaginary part is 0, where b is equal to 0. So all the math you've ever done prior to section 5.4 just involves complex numbers where b is 0, but it doesn't have to be 0. Okay? All right, so the complex plane. This is no big deal. How do we graph complex numbers? How do we represent them? Now, we can't graph complex numbers on the xy plane, because on the xy plane, the x-axis is a real axis. No, it's only for real numbers, and so is the y-axis. Going way back to your early discussions in math, you talked about a number line. Well, that's all the x-axis is a number line, a real number line. So is y. If I want to graph complex numbers, I need the complex plane, which is just like the regular xy plane, the regular Cartesian plane. Only instead of an x-axis and a y-axis, we've got a real axis and an imaginary axis. And all we do is just graph A on the real axis and B on the imaginary axis to get a point. So for example, very simple. If I want to graph the complex number -2 plus 5i, what's the value of A? -2, right? That's the real part. So I'm going to go over to, if I want to plot this, I'm going to go over to +2, or -2, sorry. And then what's the value of B? 5. So I'm going to go up 5, and so it's right there. The coordinates would just be -2, 5 in the complex plane. So right, so all this is just the value of B. The imaginary axis is just plotting the value of B. The real axis plots the value of A.
So A and B are like X and Y.
Just like X and Y. Okay, no big deal. So if we look at a couple quick examples of that, let's look at, we don't have to look at even all 4. Let's just look at a couple. Well, the first one we said was right there. Back 2, up 5. Where's the second one going to be?
Over 2, up 2.
Over 2, up 2. Okay, what about the third one? Over 4, down 3. And you get the idea. Okay, and then back 4, down 3. You got it. Okay, no big deal. So adding and subtracting, multiplying, dividing. Adding and subtracting, we talked about this, couldn't be easier. When you're adding and subtracting complex numbers, all you're doing is just adding up like terms. That's it. So for example here, if I want to add these complex numbers, think of the I like a variable. What are the like terms here? Well, -1 goes with what?
3.
3. I don't need the parentheses here, do I? Because there's nothing in front. The numbers in front of the parentheses of the quantities are both 1, so I can get rid of them. This is just the same thing as saying -1 plus 2i plus 3 plus 3i, and I'm just going to group the like terms together. -1 and +3 gives me 2. Right? 2i plus 3i is 5i, because those two go together. Done? Okay. Okay, so there we go. Now, what about something like that? Now, I want to do it my way and not the board's way on this one, so ignore what they do. I think the easiest way to do these is to distribute the negative sign so we can get rid of all the parentheses and then just add up like terms. So that first set of parentheses doesn't do anything. I've got a 1 out in front, so I can just get rid of them. I've got my 2 minus 3i. But the second set,
-3.
now look, I've got to distribute that -1, right? Good. -3 plus 7i, and then it becomes a problem just like the first one. I simply combine like terms. 2 minus 3 is -1. Negative 3i plus 7i is 4i.
Ah, it's
Done. Yeah, no big deal. Very simple. Adding and subtracting complex numbers, nothing to it. Okay, multiplying is really not much harder. And we could even do a hard one. This wouldn't be that hard, would it? All I would do is just distribute the negative sign, distribute the 1, do nothing, and add like terms, right? Nothing to it. Okay, what about multiplying? Let's take 2 examples. Okay, what if we have negative I times 3 plus I? What do you think? What if those were x's instead of i's?
Negative 3i plus negative times 3.
Okay, we can distribute the negative I, right? And if we do that, we're going to get negative 3i minus I squared.
Not I squared, just 3.
Good. Whenever we see an I squared, we can replace the I squared with negative 1, just like we did before. So then this is going to give us negative 3i minus negative 1.
so plus 1.
Negative 3i plus 1. But then the last step is we want to turn this thing around. We want to write this in standard form. So we're going to write the number first and then the I term.
1 minus 3i.
So, yeah. So we get that. 1 minus 3i. Okay. Okay, what about something like this? What do we do with that? Yeah, we just FOIL it, just like we would with x's instead of i's. We're just going to FOIL it out. So if we do that, first times first gives us negative 12, outside gives us negative 4i, inside gives us negative 18i, and last gives us negative 6i squared. But what's I squared?
Negative 1
Negative 1.
So it would be 6.
plus 6.
Yeah, so we're going to get the, these 2 terms. That's no big deal. Look, we can combine the I terms. And then I get 2 terms that are just non-I terms. They'll be like terms. So negative 12 plus 6.
Negative
Yeah, negative 6 minus 22i. No big deal. So multiplying, very simple. Okay, now where it gets, and this isn't hard, but adding, subtracting, super simple. Multiplying, pretty darn simple. Dividing, a little bit tougher. When we want to do something like, say, this. Okay, so let's say, okay, so if we want to multiply this thing out, or divide this out, I've got quotient of complex numbers. The complex number 3 plus 11i divided by the complex number negative 1 minus 2i. The rule is, my goal is when I'm all done, I want to have something in standard form. So I want to get some answer that looks like that. Okay? How do I get there? First thing is I got to get rid of the complex number in the denominator. Now, we did this kind of stuff with square roots in chapter 3, or in section 3. If you had something like this, what if you had the square root of 11 halves? We know how to deal with that,
You
right?
change them into their own and you multiply both parts. And the bottom by the square root of 9.
Okay, good. So we can split it into separate square roots. If I have a square root stranded in the denominator, a radical in the denominator, then my way of getting rid of that, remember, was to multiply both the top and the bottom by that square root. And then square root of 2 times the square root of 2 is just 2. On the top, I get the square root of 22. Done. Right? I got the radical out of the bottom. Now, how do we do that with these guys? A little different. Instead of multiplying the top and bottom by a square root, we're going to multiply the top and the bottom by the complex conjugate of this number. So it's going to be the same complex number, only with a different sign between A and B. Here I've got a minus sign, so I'm going to multiply by the same number with a plus sign. So, that guy. Okay, now what happens if I do that? I'm just going to FOIL those out. On the top, let's look at the top. So if I multiply straight across here, on the top I'm going to get, first times first gives me negative 3, outside gives me plus 6i, minus 11i, plus 22i squared. Okay, so then we can turn that into, we know that the I squared is a negative 1. So I'm going to get negative 3 plus 6i minus 11i minus 22. And so if I combine like terms, negative 3 and negative 22 is what? And then 6i minus 11i.
Negative 5i.
So there's the top. Okay, top is done. What about the bottom? When I FOIL the bottom out, because these are complex conjugates, look what happens here. First times first gives me 1. Outside gives me negative 2i. Inside gives me positive 2i. And then the last term is negative 4i squared. Every time you do that, the o and the I are going to cancel. That's why we did it. So those I terms go away. I squared is negative 1. So on the bottom, I just get negative 1 plus 4.
So you got 3.
Oh, sorry, positive 1, not negative 1. So 1 plus 4 gives me 5. Okay, and now I can just divide it out. Now I can split this up into separate fractions. So let's see that happen
Minus I.
here instead. So we left off right there, right? Now if I want to split this up, I want this to look like A plus BI, so I got to split this into separate terms. If I have a common denominator, I can just split that apart into 2 fractions instead of 1. So I could write that as negative 25 over 5 plus negative 5i over 5. And then 25 over 5 is just 5, so I get negative 5.
Minus I.
5i over 5, the 5's cancel, I just get an I, right? So I get negative 5 minus I. Done. So now it looks like a standard complex number. So dividing, it's a little tougher, but the trick that you use every time is just multiplying top and bottom by the complex conjugate of the bottom. And it'll always work this way every time. Okay, so even that's not so bad. All right, last issue, and it's pretty minor. The absolute value of a complex number. Now what this means, this is just, it's not really, absolute value is a misnomer. It's not called absolute value. The book calls it that, so we'll call it that. But what it really is, it's called the modulus.
I'll stick with absolute value.
Okay, so the modulus. What that means is just the distance the complex number is from the origin in the complex plane. Okay, so for example, let's take this guy. If I have a complex number a plus bi in the complex plane, think what that looks like. In the complex plane, here's my imaginary axis, so that's B. Here's my real axis, so that's A. If the complex number out here, A plus BI, if we plot that in the complex plane, then this distance right here,
Is the modulus.
okay, that distance, isn't that just the hypotenuse of a right triangle? Now, the coordinates of this point right here are over A and up B, right? That makes sense, because that's how we plot a complex number in the complex plane. The A value is how far we go on the A axis, the real axis, and the value of B is how far we go on the imaginary B axis. So then in this triangle, that's A and that's B. So by the Pythagorean theorem, what is the length of that hypotenuse, which is the distance?
C.
Square root of,
A squared plus B squared.
right?
Which is C. Squared.
So we know that that modulus we're looking for, that absolute value, is just given to us by the Pythagorean theorem. It's the square root of A squared plus B squared. So that's our formula, right? There it is. If I want to find the modulus of, say, this is easy. If I want to find the modulus of negative 2 plus 5i, it's just the square root of negative 2 squared plus 5 squared. Well, what's negative 2 squared?
4.
What's 5 squared?
25.
4 plus 25 is 29. Square root of 29. That's it. Okay. Make sense? All right. Wow. That was record time. That's pretty good. Okay, let's go to 332.